Okay, thank you, Chairman, and I appreciate this opportunity to be with you on this session of this AGU4 meeting. And good morning, professors, distinguished members of the AGU, and ladies and gentlemen. My talk is about solar velocities and the melting of the iron nickel silicon system at high pressures and shock loading. This is a joint research completed by Hiroshima University and China Academy of Engineering Physics and Southwest Jordan University. And I have divided my presentation into 4 parts, including introduction, material methods, experiment results, and discussion and conclusions. Let's start from the part 1. As we know, based on the seismic operations, we know the Earth is a linear structure from top to bottom. They are crust, mantle, outer core, and inner core. Our focused outer core is in liquid state and is mainly composed of iron, nickel, and we allowed with about 10% net elements, such as the sulfur, silicon, oxygen, carbon, and hydrogen. And based on the seismic operation, we know they tell us the density and the solar velocity as a function of pressure of depth. So if we have the proper vertical of the conversion of outer core, it should match to the seismic observed density and the solar velocities as the core conditions. Although several light elements have been proposed geochemically as possible candidates mentioned above, in the core, the assessments of the still remains controversial at present. So, due to the outer core is surrounded by silicate mantle, silicon has long been considered to exist potentially as the major light elements in the outer core. So, and enhanced by the high solubility in iron and iron silicate intersections at core mantle boundary and recent silicon isotopic data. Here, we conducted new experiments of density, solar velocity, and melting behaviors for iron nickel silicon model core composition by shock wave that can reach to the core compressors. Then directly compared our relations with the observed seismic data. And we have used the starting material as iron 9% nickel and 10% silicon in systems. And it was scintillated from mixed powders of iron, nickel, and silicon at about 1,000 degrees under vacuum. The average density is about 6.85 gram per cubic centimeter by the Archimedes methods. And we have analyzed it by the APMA and the macro XRD. And these figures shows the backscattered natural images and XRD patterns. And based on this analysis, we know our study material is mainly composed of the iron nickel 3 silicon, ECC iron nickel silicon, and FCC iron nickel. And a series of experiments were designed and conducted using a 2-stage gas gun up to a pressure of about 280 GPa. And these are the schematic setup of our Hognute and solar velocity measurements. And they are flare and target and Neisler flow rate, respectively. We have used the iron tantalum of tungsten as our flare. That their impact velocity we are measured by electromagnetic method. And the solar velocity of the target we are measured by pin systems. In order to measure the solar velocity of our sample, we have used the optical analyzer method. This method actually is based on a relationship between the velocity and the distance that a reflected refraction wave will overtake the shock wave in target. So if we when we measure the overtake distance, and we can use a relationship and to get the refraction wave velocities. This refraction wave velocities is the solar velocities we wanted. And so we have used the target with 4 steps and with 4 steps of 4 different thickness, and wave profiles of the 4 steps were recorded simultaneously and to fit the overtake distance. And this is our experiment results, and this is our measured shock Hognute data of our sample. And this Hognute data is based on our measure the impact velocity and the shock velocity of sample by the impedance matching method, and then get the shock coordinate. And our results is consistent with the previous determined iron silicon by shock. And compared with the previous iron nickel and iron silicon system, we know and adding the nickel into the silicon, it cannot affect the density at high pressures significantly. And our results is consistent with the iron nickel system. So, and this net shows our measured sound velocity along this Hognute by optical analyzer method. And the next figure shows the results. And we can see there is abrupt changes along the Hognute. It indicates at 140 GPa and at 183 GPa. And they are the onset of melting and the complete melting of our sample respectively. So these 3 points indicate the solid longitudinal sound velocity, and these 4 points indicate the liquid bulk sound velocity. And this point is located at the partial molten. And when compared our results with the pure iron and iron oxygen sulfur system, we can see the onset melting pressure of our sample is significantly lower than the pressure and close to the iron oxygen sulfur system. That indicates indicating substitution of silicon, sulfur, and oxygen into iron, or can make the melting more easily. And because the outcore is in liquid state, so we pick the bulk sound velocity in molten state and compared with the pure iron and seismic data and other molecular compositions. And the result shows our iron non-nickel tin silicon has significant faster bulk sound velocity than the pure iron and the iron nickel system, and slower than the oxygen-rich iron 8 oxygen 2 sulfur. It is located between the iron 8 silicon and the iron 2.2 oxygen and 5.3 sulfur. And the results also show nickel has no significant effect on bulk sound velocity, but lead elements like the silicon, oxygen, and sulfur all can increase the bulk sound velocities. So a comparison of our iron nickel silicon system and the previous iron oxygen sulfur indicates the presence of significant amount of oxygen strongly increase the bulk sound velocity, where the silicon and the sulfur may have a similar and moderate effect on the bulk sound velocity in the molecular compositions. And because the shock wave will make the sample temperature increasement, so and the temperature also is a very important factor. So we have calculated the shock temperature and extrapolated the melting temperature to a melting core. This solid core is our calculated shock temperature, and this dotted curve is the extrapolated melting curve by the Lindemann law. And this result, compared with the previous determined melting curve, give a melting temperature about 3,700 Kelvin at the core mountain boundary and 5,200 Kelvin at the inner core boundary respectively. So the melting temperature at CMB and SAB will be depressed about 300 to 500 Kelvin and about 6 to 1,000 Kelvin by the about 10% silicon compared with those of the pure iron. And because we also make thermal corrections to our measured bulk sound velocity and Hognute to compare directly with the seismic data like the prime models, and using Miangyang gradation theory. And the result shows the density and the piezo relations of our liquid iron nickel silicon is consistent with the prime with just about 1% discrepancy. And the bulk sound velocity and the density relationship, the bulk sound velocity is just is slightly slower by 3% at the CMB and verges to the prime at the ICB. And so the density and the bulk source data of our sample tell us and the iron non-nickel and 10 silicon and iron 2.2 oxygen and 5.3 sulfur both are close to the prime. But the oxygen rich iron 8 oxygen and 2 sulfur is not due to the too high oxygen content. So oxygen rich would not reproduce the seismic data, but as a result, the silicon-rich and sulfur-rich composition may be selected as the outcome just based on the geophysical point. And because currently there are some geochemical and cost chemical constraints give us upper limit of sulfur just 2%. So the silicon will be the most popular candidate among the sulfur, just silicon, oxygen, and sulfur in the alcohol, from both the geophysical and the geochemical point. And our results also may support the heterogeneous accretions models during the Earth formations, which predict about 8% silicon and about 4 to 5% silicon in the Earth's alcohol based on the metal silicate partitioning data. And we also predict the iron 5.4 nickel and 6% silicon and 2.1% sulfur and 0.9% oxygen by a mixture of iron, oxygen, sulfur, and iron, nickel, silicon systems. And this is the predict bulk source and density relationship. It has more consistent profiles with the seismic data in the whole range of the outcome. So finally, we prefer a molecular composition of liquid iron nickel with 9 elements of 6% silicon and 2% sulfur and about 1% oxygen to satisfy all the current requirements imposed by the experiments, seismology, and geochemistry, and molecular of the earning composition. That's all. Thank you for your attention.
You have time for some questions? Yes, please.
What was the porosity of your samples, and what was the average particle size that you sintered them?
Pardon? Sorry?
The porosity of the samples, what was the porosity, and what was the particle size of your sintered samples?
The central samples, yeah. Central, okay, can you turn back to this sample?
To go back. How far?
And the starting material, the XR, EPMA and XRD figure, yes? Yeah. It means the black area.
Okay, so what is, can you get an equilibrium sample?
And based on the EPMA analysis, and I also have supporting information about every point. There are several points from the point 1 to point 8, there are several points. And every point, I have EPMA data on this figure, but in the supporting information. Okay, and this is the every point's chemical composition and possibly phase. So the most parts are the main components is are this phase and several small parts about iron silicon systems. Okay, because our focus is in the liquid state after melt, so it may be homogeneous after melt.
So you calculate that time scale?
You mean the shock pressure time scale?